Welcome back, YouTube. Can you tell me what's going on in this picture? Give up? It's an electrical engineer ordering 3 beers. If you didn't get that joke, you might as well turn off. This is the network from the first video that we set up. We have a Siemens 1500 PLC set up as a controller over Profinet to an adapter configured in this Net Tap 151 device from Hilscher. We have an adapter port configured through Ethernet IP talking to a compact Logix. We set up a bucket of bytes transfer between the two. This is the Siemens side, byte by byte, the 0 through byte 11, and the Rockwell side, where we have 2 data structures that were defined as part of this adapter, added with a EDS file that came with the protocol adapter, and then configured to have 12 bytes. The only type we were allowed to have is a small integer. The signed integer, or a small integer, it is a signed integer, and it's a byte data type, and they take away one of the bits of the byte for a signed bit. So we illustrated that last time when we tried to send a number larger than positive 127, and it's telling us no, we can't do that with that data type. With one of the bits being gone, we can go from negative 128 is the smallest number it'll accept, and then up to positive 127. Let's take a look at that largest negative number as it gets transferred over. You see we're interpreting it here as a plus and minus decimal. Let's take a look at that in the bit format, binary. So you can see that the sign bit is set, and we have all the bits 0. Let's go back with a small integer and enter the largest positive number, and that will be the negative sign bit is off, and you can see all the other bits are on. So that's the largest number that we can represent in that byte data type. So our goal for this video is to send across more useful data types. We have to overcome not only that signed byte, when we combine those, we have to get rid of that, and we have to consider the byte order. Let's take a look at a quick picture on the byte order. Siemens uses what's called a big endian byte order. The most significant byte from this larger data type, this would be a double integer on the Siemens side, or possibly a real. And the highest or most significant byte is stored first in memory. So if you think big endian, the big end goes first. And if we think of this data mapping directly across to the Rockwell side, which uses a little endian convention, you can see that most significant byte from that word will end up here, which will end up in the least significant byte of the Rockwell data type. So we've got those two things to deal with, that each byte itself is signed, and each data order is going to be wrong if we send it across directly across. I'm bringing up the Siemens Net software. I am going to take a look at the configuration just to remind you that we mapped all the bytes one for one. And we have this tool here where we can map input bytes from one side to the other, and we have data flowing in the Siemens to Rockwell direction, and we also have bytes flowing from the Rockwell to the Siemens side. This will be a tool we're going to need to use in a little bit to fix that byte order problem. We're also going to need to use another command in order to, and actually some ladder logic in order to combine these data types. Okay, so let's take a look at the data types in the Siemens PLC. So the first thing that I always teach in Siemens, all of our structures are set up as byte structures. Every offset that you see here is a byte offset. This is input byte 0, input byte 1, output byte 0, output byte 1. No matter if you're looking at our input, our outputs, our data blocks in their simplest form, the flag memory, which would be our M memory, everything is designated by a byte offset. And if you use a larger data type from that structure, you are grabbing more than one byte. First data type I'll talk about is a word. A word is an unsigned concatenation of 2 bytes. In that word, we can store the integer data type. Most significant bit, which would be here, is broken off, so you end up with a sign bit there, and the rest of the bits are used as counting numbers, and that's what you'd call the 2's complement representation of a number, so that we can represent negative numbers. That would be for an integer. The other 2 data types that we're going to go over fit inside of a double word, and that is a 32-bit structure. Inside of a 32-bit structure, we can put what Siemens calls a double integer, or we can also put a 32-bit real number that is encoded with the IEEE format. We'll look at that a little bit later when we're doing it. But just to get started, what we're going to do is put a word here into Q word 0. That will give us the ability to send across a double integer, an integer in this first word. So I defined here Q word 0. I'm allowing this to display signed. And what I did here is I took this from signed bytes to just bytes. So now in here I can represent 0 through 255. Let's just take it here. Let's put a 0 in here, and we'll go ahead and write that to the PLC and see what happens to this word here, these 2 bytes. So 0, 0 is 0. If we put a 1 in, take note that the least significant byte of the 2, which is big endian, big N first, is here. So if we put a 1 in, we're sending a 1 across on QB1. And if we looked on the Rockwell side, you can see that we are bringing across a 0 and a 1 in that order. If I put a large number in, 32, 7, 66, something right up near the top, and I write that, you can see that we end up with larger numbers in both of the bytes going across. We can also represent a negative 32, 767 or 676, and you can see we end up with other numbers here. If we look at this in decimal, positive and negative, or I'm sorry, in binary, you can see that that sign bit here is set, and that means a negative number. That's kind of the under the hood look, but what we're going to do is just leave this in decimal format and see it as it travels over to the control logics. That 128 is now showing up as a negative 128 here in this signed integer, or signed small integer, and a 92, which is the same. What we need to do is convert that number back into the original number, and what I found to do that is going to require a little bit of programming and another data type to hold that. So if we go ahead and create a new tag on the fly here, we're going to make it an integer from Siemens. And it's important here to change the data type before you close this. So double checking this, I have a integer data type. It's an integer from Siemens, and I'm going to create that tag as just a base tag in the controllers. So now I have that to program with. I will open up the main program here and attempt to put a copy command in and explain how that copy command works. It works on a bit-by-bit copy basis, so it will ignore those signs. So we're going to edit here in the main routine. We're going to go to File and Miscellaneous, and we're going to put in a copy. This copy command you can see how much control logics I do, is going to copy from our source, and that's going to come from the net tap structure. And we're going to start at data byte 0. And we're going to copy over to the destination of the integer base tag that we set up. And basically the length is always the number of this data type structure bytes. This integer is made up of 2 bytes, so it's going to basically copy 2 bytes from this source to this destination, but it's actually just one integer, so I'm going to put the number 1 in there. Okay, so I will accept that edit directly in, and if we just hover here, we can see we're getting negative 10,151, which doesn't match up with our 23,000 that we sent across. What's going on, as we talked about, this byte here is going into the, which is our most significant byte, is going into the least significant byte and being interpreted. If we go back to the controller tags, we can see that that is being interpreted as negative 10,151. So that'll never do. So what we need to do is get those bytes swapped around in transit, if you will. So we're going to bring up our NetTap configuration utility again. And what we're going to do is swap the first 2 bytes going from the Profinet side to the Ethernet side. So we take a look at the arrows here. I can grab the first 2 bytes and highlight them with the shift and then remove the links. And then up here I need to reconnect them. So I'm going to connect byte 1 to byte 2. And remap, map signals, and byte 2 to byte 1. And map the signal. Apply those changes and then re-download. Okay, it's going to reboot there, and when we come back, we should have remapped signals between the Siemens and the Rockwell. So let's take a look at that. Should be happy. And we're sending 89 across in byte 0. And if we look at it here, and you can see now that 89, let me just get that out of there. The 89 is now in the second byte. So if we go back down here, again, remember our PLC code doing the copy of one integer starting at data 0 in the input, and that maps into the integer from Siemens. And we'll go back to the controller tags here and take a look. Integer from Siemens is 2300. That matches up with the number that we're putting in here. Let's put in minus 32,000 and make sure the sign bit and the whole works is making it across. So negative 32,000 interpreted here as an integer. Going over to Rockwell, you can see that we've recreated that 16-bit signed integer. Next, we're going to take a look at a double integer. So let's come back here. We are going to appropriate 4 bytes starting at Q byte 4 for a double integer. So I will call out a Q double word starting at 4 and make that signed. Let's quit injecting this data. So 4, 5, 6, and 7 need to be clear. We can repeat that demonstration. First of all, if I put a 0 in there, this double word here is going to take up 4, 5, 6, and 7. So I do have to clear one more byte out so that I'm allowed to force this number. And once actually it's not a force, it's just a write. So if I write 0 in there, that clears out all of these bytes. If I put a 1 in here, the least significant byte is the last of those 4 bytes. And if I put a -1, you can see that we have set all these bits through here, including the sign bit at the top here. So that's the data structure that we want to send across, similar to what we did with the, let's go to unsigned. This is similar to what we did with the integer. So let's continue on with this. And let's use the same tools over here on the Rockwell side. So in the main routine, we're going to add another copy command. So this time our source is going to be Net Tap data byte 4. And we're going to need a destination. So we're going to name another tag here. We'll add a new tag, and it's going to be a dint, which is really a that would be a dint on this side as well. A double integer dint from Siemens. Here's a double integer. We're going to create that. And then back here on our program, we're going to target dint from Siemens. And again, it's only one dint long. That's the edit. Let's just compile that in. And if we hover here, we see we're getting the -1. That's kind of a coincidence. Let's go back here and put in a more reasonable number. 100,000. Let's write that. You can see that gets encoded through these bytes starting at 4 here. So there's a 1, a 134, a 160 is the raw bytes coming over. And if we hover here, you can see we're getting just a crazy number there. So again, we're going back to our data mapping to make this right. So I need to go offline. Disconnect. Go to the config. It's coming up there, okay. And to the map. Again, data from port 3 to port 2, down here at the bottom. 3 and 4, and it's actually byte 5, 6, 7, and 8, because we started at 0 in the PLCs and it started at 1 here. So we're going to unmap those. Simply reverse all the byte orders. So we'll map 5 to 8, 6 to 7, 7 to 6, and 8 to 5. Okay, so that remapped those. They show up down at the bottom there. We'll apply those changes. And while I'm here, I think let's just go ahead. The next data type that we're going to do is also a float. And that's going to be at 9, 10, 11, and 12. And that's a 4 byte data structure. I'm going to remove those links and remap those as well, so we don't have to come back here. So 10 to 11. 11 to 10. And 12 to 9. Mapped. Apply. And download. And it's back. And done. Now if I hover here on the double integer, you can see that there's 100,000 coming across just as we sent. Let's try a negative 100,000 and then write that. Negative 1 million. Go over to the Rockwell side, hover here, negative 1 million. And back to the controller tags, negative million. The last data type we're going to do is a float, and as we did in the mapping, so we use 4, 5, 6, and 7. Let's clear our writing of 8, 9, 10, and 11, and we will map another Q double in at 8, and we'll designate this to be a floating point number. And that's kind of garbage in there right now, but let's just put in 1.0 and look at how the encoding works here. This encoding is really unintelligible unless you're using the PLC to decode it. You can see that there's 63. Let's look at that. Let's look at these guys in decimal. So these last 4 here are really unintelligible. The encoding is based, as I mentioned before, is based on a IEEE format. So here it is. Hopefully that stays on top. Yep. So this IEEE 754 is used by Rockwell and Siemens. We've set up a floating point number. The encoding doesn't make much sense here, but this is the format, and this is the IEEE 754. Just like before, they're using a sign bit, but the rest of this number is heavily encoded based on number of bits, and it takes a complex formula to actually decode that, which your PLC does. This is used the same on both sides, and I believe it's part of the 61131 IEC PLC spec that most modern PLCs follow. So if we look at it though on the compact logic side, We're going to need another data type to put it into. I'm going to add a real data type now. So we'll create a new tag. It'll be a real from Siemens. Data type will be real. And we'll create that controller tag. Going back to our program, we'll need to add one more copy. And we'll take the Net Tap data, the last 4 bytes, this structure. So it'll be 8, 9, 10, and 11. So it's starting at 8. Real from Siemens will be the destination, and it'll be one real long, which will grab those 4 bytes. Let's just go ahead and accept that. And remember, now we already did the mapping. So the data is 1.0 coming across, so everything is actually good. And if we go back to our controller tags, we can see that we've completed those 3 data types. Let's just check out the float a little more. 3.12. Go back to the Rockwell side. Let's try writing it first. There it's written. And we have 3.12. Check out the sign just to make sure everything is going. Negative 3.14159. These data types will hold 6 or 7 significant digits. If you keep typing beyond that, it's just going to round it off, as you can see. We'll write that, and we have now a negative pi number. Its style is actually called float here, so it looks like they interchange those data types as well. So that takes care of the direction, 3 data types going from Siemens to the control logics. What I'm going to do lastly is encode 3 tags from the compact logics and send them to Siemens. To get data going in the other direction, I'll start again with making a new tag. Start with the integer again. And we'll make it integer to Siemens. Create. Once again, we're going to rely on the copy command to copy this 16-bit 2-byte data type into 2 of our output words this time. So we'll map those at data 0 and data 1. So let's go back to our ladder and we'll start a new rung to handle data going in the other direction. So once again, copy. So this time the source is going to be our integer 2 Siemens. The destination is going to be the Net Tap out byte, but there'll be a slight twist this time. We'll go to Net Tap out data 0. Now the length again is based on the destination. In this case, we want to write 2 bytes. We have to actually put a 2 here instead of a 1. And let's accept that edit and see how it's encoded it for us. We'll have to go back to the controller tags to see that. So integer to Siemens 0, mapped as 0, 0. If we put a 1 in there, you can see that it used a little endian, the little end first, and it put a 1, 0 there. So we're going to go take a look at that on the Siemens side, and you see that we have a 1, 0. Let's let Siemens interpret that 1 and 0. Let's insert a few rows here so we can keep it all in view. Let's interpret input word 0, and we'll interpret that as a integer data type, decimal plus minus. So what we're seeing is 256. We entered a 1 and we ended up with 256 because of the byte order swap. So we're going to head back for the last time to the configurator, and we're going to flop all of the bytes for this direction the same way that we did. First disconnect. Signal mapping. And this time we're going to be looking at the data going from the Ether IP side to the Profinet side. And let's just go ahead and unmap all 12 bytes here. Well, actually the first 2 bytes, remove the link, and then the 8 bytes for our 2 larger data types, remove those. And everything's the same. We're going to take byte 1 to byte 2. Byte 2 to byte 1. Recalling what we did, 5 to 8. 6 to 7. 7 to 6. And 8 to 5. Lastly, 9 to 12, I believe. Yep. Nine to 12. 10 to 11. 11 to 10. And 12 to 9. You can see that's a lot of manual work there to set up your data transfer. It's possible this could be done in the PLC, but not as straightforward as the approach that we've taken. We're going to download that mapping for the last time. And it's back. All the lights are green. Now we've reversed these bytes, and we're getting a 1 coming across. Let's put something integer to Siemens. Let's put a larger negative number in there. It's encoded here, and it's interpreted back here as negative 32,000. So next will be, I'll do this a little quicker. Everything's really just the reverse order from what we did before. 0 and 1, 2, 3, 4. So we have input word 4. interpreted as a integer, and the last one will have a input double 4, and that's a input double 8. This one will be interpreted as a decimal number, plus and minus. This one will be interpreted as a floating point number. And we'll go back to the Rockwell side. We're going to add 2 more tags. We're going to take a dint, 2 Siemens as a dint, create that. And lastly, real 2 Siemens as a real, create that. So we've got these 2 tags here. Go back to 18 here. We'll have two more copies. So our source will be Net Tap. I'm sorry, our source will be the dint 2 Siemens. The destination will be Net Tap output, and that's Net Tap output 4. And we need to copy 4 bytes there. And this will be the real 2 Siemens, and this will be Net Tap output data 8, and that will be also 4 bytes. So we'll just do both of those in one shot here and get it done. Go back to our controller tags and look at the data. 2 Siemens. The double integer, let's send across 1,000,000. And the floats, let's send across 3.14159. So we're looking for those 2 numbers. If we look here, we've got 1,000,000 coming across in our double integer, and we've got 3.14159 in our float. So that pretty much takes care of data types of int, double int, and float in both directions. Lastly, I just thought of this, we could tackle a bit. Let's just see if we want to use some of those as bits. If you remember, we left QB 2 and 3 alone. We haven't added those to any part of our program. So let's look at those as binary, and let's add a Q. Let's see, Q2 2.0 here. Right now that that bit is set. If we modify that to a 0, you can see that bit went down. This bit here is addressed directly as Q 2.0. Again, any of these tags or any of these values that I'm using here, direct memory access, you can make a tag that simulates those, similar to what we did over on the Rockwell side. So 2.0 bit coming across. is going to be mapped directly to that third bit in the telegram, and then coming here, that's going to be mapped to these data bits. So we can you should be able to directly, let's see, that's the output, sorry. Let's go to input 2. You can see that bit there is off, but in our code you can directly access or alias that bit. If I force that back on, I'll modify that to a 1. That'll go true, and you can see that bit here is now true, and that could be used on any of your code here. Add wrong. We should be able to directly access that Net Tap input. Data 2 bit 0. We're directly looking at that right now. You can see that bit is on. And if we go back here and turn that bit off, it's gone off here. So that should do it for this video and the video series. Again, if you have any questions or comments, please leave them below. I'm sure there's a better way to do this. Please feel free to make a comment. See you in the next video.